Hello and welcome to the ELE 402 graduation project video. I am Emre Kerim Kaymak and I will be your host for the first half of this presentation. This project is about the development of a respiratory sound classifier using open source infrastructure. This means taking a sound file, just like this obtained from a stethoscope, and classifying it on whether it is a normal waveform, it has a crackle or a wheeze in it, or even both. To do so, we have developed convolutional neural network models from my part and decision tree models from Ömer's part, using the 2017 HP and the 2019 Hacettepe datasets provided to us by our professor. So let us start with my part, the convolutional neural networks. We start by filtering the noise with a notch and a high-pass filter. Then the waveform is transformed into a MEL spectrogram which has intensity values in it. This spectrogram is then convolved with a filter called a kernel. This process is repeated several times with the use of an activation function, and at last a flattening layer is used to get an output. The error is then corrected by an algorithm that we call the backpropagation algorithm that basically takes the derivative to compute errors. Now let us see a demonstration of a trained model. Here we can set a model to be used and the sound file to be classified. After running the script, we obtain several important graphs such as the waveform, a Fourier transform, as well as the MEL spectrogram corresponding to it. At last, we see the prediction that the model has made with the confidence values. The model has predicted that this sound has a crackle in it with the 86% level of confidence. And indeed, this model was correct here. Now, let us see the results that we have obtained from the actual datasets. Here, we have the results of the HP and Hacettepe datasets, as well as the results of them combined. As the HP dataset is made of segments, while the Hacettepe dataset is composed of long sound files, they don't get along very well. And due to this, individual models performed significantly better at around 60%. It must be said that these are unfortunately 10% lower than the goal set at the beginning of this project. Now, one might ask on where the error occurred. It is unfortunately difficult to figure out since neural networks works basically like a black box, where we don't know how the model decides on the weights and the biases. Thank you for listening to me, and now I am passing the microphone to my teammate Ömer İbrahim Toka.
Thank you, Emre. I'll take it from here and talk about my part of project. As Emre indicated that we are working on two different datasets. One is the ICBHI 2017 dataset, and the other one is from our university, Hacettepe 2019 dataset.
Before feeding the data to the model, let's briefly talk about signal preprocessing. The first step in our code is noise reduction. Raw respiratory recordings often contain low-frequency background noises, such as heartbeats, which can mislead the model. To prevent this, we implemented a Butterworth high-pass filter, as you can see on the screen, effectively removing all frequencies below 150 Hz from the signal. With the cleaned audio, let's move on feature extraction. To help the model understand the audio mathematically, we use the Librosa library to extract key features from the sound signals. We calculate critical metrics like MEL frequency capsule coefficients, zero crossing rate, and spectral centroid. We then compute statistical values such as mean, maximum, and standard deviation of these metrics to create a robust, one-dimensional feature array for each respiratory. With the data fully prepared, let's dive into our machine learning model. After splitting our data into 80% for training and 20% for testing, we sent this data to our classifier, XGBoost. XGBoost is an algorithm that builds highly accurate predictive models by combining multiple weak decision trees into a strong ensemble. To get rid of class imbalance during training, we scaled our features and assigned specific class weights to the model. Finally, let's review the outputs and results. Once the training is complete, we evaluate our model using the unseen test data. The output generates a comprehensive classification report, showing the overall accuracy of the system and how accurately it detects each specific respiratory anomaly. Finally, the confusion matrix you see on the screen provides a clear visual representation of which class model predicted correctly and which classes it occasionally confused.
Thank you for listening to me.